what is machine learning? And as you can see up there in that cartoon, we can't really talk about artificial intelligence without talking about machine learning. But, you know, the joke there is that artificial intelligence sounds a whole lot nicer or exciting or just fascinating. But when you talk about machine learning, that maybe sounds complicated, too hard, not as science fiction-like, and it won't attract as many people. But you really can talk about artificial intelligence these days without understanding machine learning and talking about it, because it really is pretty much the same thing. We wouldn't have these AI tools if we didn't have machine learning. And machine learning is behind pretty much all the AI that you use. So what is machine learning? Well, machine learning is a type of artificial intelligence where a computer does something quote-unquote intelligent using a certain type of algorithm, a machine learning algorithm. Or you could say machine learning is programming a computer to make predictions by quote-unquote learning patterns from data. Or you could say machine learning is a computer program that improves on a task in a way that sort of mimics how humans learn when humans learn with repetition and pattern recognition. So notice all these caveats, all these quotations, right? Artificial intelligence, we think it's like humans, but then when you look into what makes it run, it's machine learning. And then you have to say things like, well, depends on what you mean by intelligent, and depends on what you mean by learning, and it depends on what you mean by humans learning, what kind of learning you're talking about. But that's what machine learning is. So with those caveats, we can say this is what it does. So examples of machine learning that you may have run into would be face detection, that helps you automatically tag your friends on your photo app on your computer or on Facebook or another social media. It recognizes through learning through patterns of data that this person goes with this name, this label. Fraud detection. Fraud detection is learning patterns of credit card activity. So if I take my credit card and I travel to Thailand, say, without warning my bank, and I buy a big flat screen TV, for example, in Thailand, it's likely to flag in that machine learning algorithm that this may be someone stole Sarah's credit card, because for one, I don't normally live in Thailand, and number two, I've never bought a big flat screen TV in my life. I just haven't found a use for one in my home. Spam filters is another one, learning to recognize what kind of email is likely spam and what kind of email is likely not spam. I've heard in some university spam filters, as much as 99% of the emails that come in get filtered out and thrown into spam. So it's really nice to have these spam filters working for us. Optical character recognition is one of the very first successful applications of machine learning. It reads numbers. The particular early application read handwritten numbers, say on a check that you deposit, but the original application was zip code, postal codes on envelopes, and getting the computer to recognize people's handwriting and then put it into Unicode characters, what they wrote, and being able to sort mail faster that way and not need a human to do it. So optical character recognition, but also, yes, when you write a check, or somebody writes you a check by hand and you take a picture of it and the bank app recognizes it as a check that you can deposit in the amount, that is also an instance of optical character recognition. So that is a transfer from handwritten letters to Unicode, right? And it's different than just taking a picture and having like in a PDF or an image, right? Because in that case, you don't have any Unicode recognition going on. And then speech recognition, which we covered already in the second week of this course, or the third week, where it learns with lots of data and repetition to transcribe the audio files into typed or Unicode text. So these are all examples of machine learning applications. So some of these we've already covered without talking about them in terms of machine learning, but you've been introduced to them and you run into them all the time. So how do we build a machine learning program? What is the workflow? Often when we talk about machine learning, it gets focused down to what happens in the computer, maybe what happens in the computer science department here at UF. But the process and of building it, the workflow of building it, starts much earlier than that. So first of all, we have to gather the data. You have to have lots of data to learn patterns from. We saw that a little bit when we talked about probability. These are statistical models. So we have to have lots of data. You have to get that data ready, right? You have to make sure, for example, if you want to learn how to build a statistical spell checker ranking algorithm, that all of your data is actually in English, if that's the language you're trying to spell for. In American English, probably, instead of British English, if you want to build it for an American English audience. So you have to pre-process that data. That in itself, some people have said, can take up to 80 to 90% of the time that it takes to build an AI thing is just working with the data. You have to annotate it. If it's a supervised or a classification model, which is what we're going to focus on, that data has to be labeled. So you have to find the misspellings, and then you have to correct those misspellings for a spell checker, for example. If you want a model that can recognize the parts of speech or the constituents in a text, you have to have somebody go through and hand and find them and mark the parts of speech. If you want to know how to transcribe from audio to Unicode, you have to have somebody take the transcriptions that already exist and align them to the audio segment where that sound is being produced. So you have to provide kind of the cheat sheet or the training data for the machine learning model, because it can't learn classification without having those annotations or supervision or labeling. With that, you can then engineer a model. So today, most people use pre-trained models, especially if they're working with English. But if you have a language that doesn't have a model, or you have a new task in a language that's never been developed before, then you're going to have to create the ideal optimal model, create that, program it, get the different parts together, you build the model. That's in computer science. Once you have the optimal architecture of the model, then you can train it. And that is, we'll talk about that more in just a second. But basically, that's where the learning happens. Once you've got a model trained as well it's going to be, that's called convergence, it's not improving any better on the data that you've been able to provide for it, then you can test it. You take some of that data out that you annotated, you don't give the computer the answer, and you say, okay, predict now. Turn your statistics from counting and dividing and ratios and turn it into a prediction now. Use what you've learned to give me now the parts of speech that's in this new text for which you do not know what the part of speech are. They haven't been annotated. And then you check it against the annotation to see how well the computer did, and then you have a measure of accuracy or goodness of the model. You say, oh, it's good enough, great, let's deploy it. If you're not sure if it's good enough, then you want to go to the last state, which is evaluate it. So, again, gathering data. We've got to get the data. The data has to be specific for the task. It has to work. Computers can't read between the lines, so we have to be very precise. So where are we going to get that data? Is it legal to get that data? Is it in the right language? What are the ethical implications of taking data from different populations or not taking it from certain populations? Pre-processing the data. What format does it need to be in? What language does it need to be in? Annotate. Well, if you want to train your model to recognize handwritten numbers, then you don't want to take handwritten examples of numbers and give it Unicode for letters, right? It doesn't make any sense. It's not going to produce numbers. It's going to produce what you gave it. So what's the task? What's the specific task? If you're trying to build a speech recognition model, you don't provide data that is translation between two languages. That may seem obvious. So up to here, you're in the area that's mostly handled in data science and in linguistics. Going on to the next part, the engineering, you're in more into computer science, so it's kind of a spectrum. Here we're getting more into the computer science side. So what kind of learning, right? So we talked about, and we'll talk about more, there's different kinds. There's unsupervised, there's supervised, there's semi-supervised, there's the old rule-based models, there's the machine learning models, there's the new deep learning models. What kind of learning? What's the optimal for the task and the data that you have at hand? And then you train it. So this is where those probabilities come in. Learning the model, and I call them fancy probabilities because they're fancier and more complex than what we covered and what we're going to cover in this course in detail. And once it learns it as best it can with the data available, then you test it. You say, how well did it learn? Is this a product I can deploy and my customers will be happy? If not, what is wrong? Why? You look at go back to the model, look at weaknesses there, you look at the predictions, why is it wrong, come up with an error analysis, come up with what you think is the weaknesses here, and then you can go back to any one of these steps in the workflow to improve the model at that point. So you analyze what's wrong, and you try to go back to the problem source and do better. Maybe you need more data, maybe you need different kind of data, maybe you need a different model or a different approach. All right, let's talk about types of machine learning. We're really only going to focus on one type, which is supervised machine learning, but we want to get an overview first of all the types out there so we can then talk about why we're focusing on this one. So there are basically, this is an oversimplification, but there are basically two ways in which machine learning, artificial intelligence, quote unquote, learns. One is supervised, sometimes referred to as classification, and one is unsupervised learning, sometimes referred to clustering. So let's look at these two. And I'll note first to start out with that both are similar in the fact that they're based on the computer finding characteristics or features that are similar across data points. So data points that are of one type should have similar characteristics or features, and those that are different should have different features. So we want to find those patterns of similar characteristics or features, and that's true for both of these models. And that's your statistics, right? What are the patterns that we find here? What's the frequent patterns that we find? What are the proportions, and how can we use that to predict? Supervised machine learning, in that case, the categories or the labels already exist. So humans have gone through and they've created them. And this can be they've aligned timestamp to the transcribed data to the timestamp on the audio file for speech recognition. They have provided a French translation for the English translation. They have provided a part of speech label for every word in the text. They've provided the correct spellings for all the misspellings. So those were done by humans, and that's where the word supervise or supervision comes from. The humans are supervising what the computer should learn how to do. Although in reality, they do this beforehand, and most of the training and the computing part, it happens afterwards. But there was human input, so that's the supervision. Humans supervise what happens. In unsupervised, we have categories that we know or we're pretty sure exist in that data, but no human has gone through and labeled them. Okay? In supervised learning, then, the model is learning to classify each data point, so each thing that you're looking at, into one of the categories that the human provide. So, for example, every word, it's going to classify every new word that it sees into one of the parts of speech that the humans provided in the training data. It's going to match every segment of the audio to the Unicode character of all the possible Unicode characters that the human provided. So for American English, that would be ASCII characters. So it knows ahead of time which categories it needs to provide, and it tries to find the best fit for each example, each data point, whatever that happens to be, to those categories, right? But in unsupervised, we don't have the categories ahead of time, so the model is just going to cluster the data points into groups that it finds similar, and it's going to try to keep the groups that are similar together and the ones that are more different from each other separate. And then the human then has to look at it and say, well, does this make sense based on what I know about the world? And there's a lot of tinkering around that you can do. Try different groups, different number of clusters, and just see which one looks best, and they're like, okay. So it's a different approach. Different algorithms, different approach to doing it. Unsupervised is much less flexible in the task it can do. It also requires a lot more data because you don't have labeling. However, the advantage is you don't have to pay for expensive human labor to categorize all your data first. All right. Those are the two main types. Here's a little picture of how those work. So supervised learning, or a classification algorithm, this is an image classification, so it's not language per se. but it's providing maybe language for images, right? Labels for the images. So in a supervised learning, a human will go through and look at all the pictures and will label, this is a duck, duck, and in this case it's a binary, so if it's not a duck, we just say not duck. So the other ones, it's either duck, not duck, and the human labels all those pictures. Those pictures, that's then the training data, right? We have the image and we have kind of the cheat sheet, the answers to it, the categories. We run that through a supervised learning model, a statistical model, and it comes up with a predictive model. That's our pre-trained model. So now we can take that model, we can deploy it, and someone can come along and bring a new image for which there is no label, feed it through that predictive model, and the model will spit out a label. And if it's a good model, it will spit out the correct label most of the time. So if it's a picture of a duck, it will recognize that's a duck and say, this is a duck. And so the computer looks very smart, very intelligent. That's supervised learning. Unsupervised learning, you can see there we start with images, there's no labels. In this case we have, well, a little bit more data available. So what's going to happen here? There's no labels. The computer is not a human. It doesn't know what a duck is and what a duck is not. How is it going to figure out what is a duck? Well, we're not asking it to tell us whether it's a duck or not a duck. This is a clustering algorithm. We're asking it to find all the pictures that look more similar to each other than they do to any of the other pictures. And then cluster those pictures together, and all the pictures that look similar to each other and not like the other pictures, cluster them together. And we decide ahead of time, so we have to have some guess at what's in the data, how many clusters we want. And so in this case, we say, well, I think there's 3 different kinds of animals based on just eyeballing the data. So let's try 3 clusters. And so in this case, the model's going to look and hopefully find that there's similarities. There's something similar about those 3 pictures that are grouped at the top. It doesn't know it's a duck, it just finds that they're similar in some way. And the middle one is different in some distinctive features from the top 3, but also from the bottom 3, or the bottom one, the 3rd group there. And that one itself is different than the others. And if there were other pictures of hedgehogs, hopefully there would be features similar enough to put them in that bottom group. And so then we can come back as humans and say, oh, okay, yeah, look through it, this makes sense. It seems like we have a good model, it's found the same kind of clusters we would, and so then we can add labels to it as useful and say, oh, ducks, rabbit, and hedgehogs. It's a little bit different here. The one we want to focus on is the supervised learning. We're going to get that predictive model out of it, and that one, as you can see, because the humans are giving the correct answer, you can imagine how it's a little bit more flexible, a little bit more useful in what you can do with the supervised or the classification algorithms. Here's an example of unsupervised learning applied to language, natural language processing. This is an application in the work of dialectology, trying to identify what dialects might exist in a country. So in this case, we have, say, information, say through surveys of lots of people, and we ask them, what do you call a sweet, flavored, carbonated beverage? And you can see there, the options that come up are soda, pop, and Coke. So soda is there out in California, up in the Northeast, in my native city of St. Louis, in the Milwaukee, Chicago area. And you can see just down there in the south part of Florida, so you can see right away why they say the further south you go in Florida, the more north you are. Coke is clustered there in the south, so that's what I grew up actually saying more often because my mom is from the south. So I had to learn how to use both Coke and soda say soda when I was with my friends in St. Louis. And then in the north, in the Midwest, and in Canada, they tend to say pop. All right, so we could get that from a survey. We can get their geographic location, which is like a label. You might say, well, that's labeled, right? That's supervised. Well, again, what task are we going for? You arrange your data for your task. We're not trying to determine where they're located. What we're trying to figure out is how many dialects they are and where those dialects are located. And to that, we need to cluster our data based on the similarities. And so this shows a nice little map of how that would work out. We just say, okay, find the clusters for soda, pop, and Coke. And it turns out it does, as we would expect, cluster nicely on the map. So So what the computer here has found out is where the dialect boundaries are, what we call isoglosses, which we didn't know before. Well, I mean, we knew, but let's say we didn't know, and that's nice. So now we don't have to guess anymore where those boundaries are. We've got them defined by the computer. So the computer found those dialects for us, and we can say, the North Midwest and Canadian dialect, the Coke dialect, the Southern dialect, and then the Soda dialect, which is kind of weird spread around. One thing that's interesting about this, which is something you want to keep in mind, this just happens to work out on a map because it is a geographical clustering. But what's interesting here is this whole idea that you can put data points into and arrange them in a way that is like a geographical or geospatial location. And think about data points as dots in a three-dimensional space. So just keep that in mind. Here it actually works out. They are on a map, and so we can see that. But we can actually take that idea of even if it doesn't have to do with geography, we can think about data points as dots in a three-dimensional space. Okay? So just put a tag on that. We'll come back to it. Here's another example of an unsupervised task related to language technology, and that is Ngrams, which we've talked about, that quote-unquote language model that we use for predictive text and chatbots and also for style checkers. Now, some people would say this is supervised because, right, what are you doing? You're counting the occurrences of the words that occur before the word that you want to predict. And so that kind of ends the label. Other people say, no, there's no human supervision, so it can't be supervised learning. We're going to simplify that task. I just want to, if you run into it, read about it. Just want you to know there's some disagreement there. We're going to do a simplified explanation, which is this is an unsupervised task because it doesn't have human labels. But we can get some information from the text, which is nice and useful. So there's the features. There's where the features come in. We can find these counts of, in this case, bigrams before each word and use that to predict, after these two words occur, what's the most likely next word? And what should we predict or generate in the chatbot? So that's an unsupervised application, or an application of unsupervised learning. But we want to focus on supervised machine learning, or classification. Because other than those few examples, most language technology, most AI is supervised machine learning. So how does this work? Well, it's kind of like this. It's kind of like our statistical model, our computer, is shown, again, we're going to go with images because rather than language, it's shown something. It's shown a data point. Here, a picture of a car. And its job is to predict the correct label. And so it doesn't know. It has a list of words that it's been given. These are all the possible labels you can choose from. And it starts out with random weights, and it spits out a random label, butterfly. And the human says, no, it's a car. And so then the statistical model of the computer goes, and says, okay, car. And then you pick up the next image, and the computer, again, doesn't know what it is, and it probably spits out car, because that's what it was weighted to learn. And you say, no, that's a butterfly. And it says, okay, adjust weights, butterfly. And it's adjusting the model during the training until it gets, hopefully, to a point where it's most of the time accurate. It's learned the probability. If you see these features in the image, then that's going to be a